Welcome to this coding walkthrough. In today's session, we'll be tackling problem number 977, squares of a sorted array. This problem challenges you to transform and sort an array in an efficient way, making it a great opportunity to practice working with arrays and algorithm optimization. Let's dive in. The problem requires us to work with an integer array called nums, which is already sorted in non-decreasing order. Our task is to return a new array that contains the squares of each number from the input, but the output must also be sorted in non-decreasing order. For example, if the input array is -4, -1, 0, 3, 10, squaring each number gives 16, 1, 0, 9, 100. However, this squared array is not sorted. By rearranging the squared values into non-decreasing order, the final output becomes 0, 1, 9, 16, 100. The goal is to efficiently compute this result while respecting the sorted order of the output. Now, let's look at another example. If the input array is -7, -3, 2, 3, 11, squaring each number results in 49, 9, 4, 9, 121. Again, this intermediate array is unsorted. Sorting it in non-decreasing order gives the final output 4, 9, 9, 49, 121. Similarly, for an input like -5, -3, -2, -1, the squares of the elements are 25, 9, 4, 1. After sorting these squared values, we obtain the output 1, 4, 9, 25. These examples illustrate how the process involves both squaring the numbers and ensuring the output array is in the correct order. To solve this problem effectively, we need to consider the constraints. First, the input array can contain up to 10,000 elements, meaning our solution must be efficient and handle large datasets without excessive computation. Second, each number in the input array can range from -10,000 to 10,000. This wide range includes negative numbers, whose squares become positive, and these positive values must be correctly sorted in the output. Additionally, the input array might contain zeros, which must remain correctly positioned in the result since their square is still 0. Lastly, for single-element arrays, the output is simply the square of that one element. There are also some edge cases to keep in mind. If the input array consists entirely of positive numbers or entirely of negative numbers, the output will naturally be sorted since squaring preserves the order within each group. However, when the input includes both negative and positive numbers, the transition between these groups needs special handling to ensure the final array remains sorted. Given the potential size of the input, we must aim for an approach that avoids unnecessary operations or excessive memory usage. These considerations will guide us as we develop an efficient solution for this problem. To solve this problem, one approach we can consider is the brute force method. The intuition here is simple: we can square each element in the array and then sort the resulting array to get the desired output. Since the input array is already sorted, squaring the elements disrupts this order, so we rely on a standard sorting algorithm to reorder them. The steps for this approach are straightforward. First, we iterate through the array, squaring each element. Then, we use a sorting algorithm, like Python's sorted function, to sort these squared values. Finally, we return the sorted array. However, while this approach is easy to implement, it comes with some drawbacks. The sorting step dominates the time complexity, making it O(n) log n, and it may require additional space, resulting in an O(n) space complexity. Importantly, this approach does not take advantage of the fact that the input array is already sorted, which means it's not as efficient as it could be. A more efficient solution is the optimized two-pointer technique. The key insight here is that while the input array is sorted in non-decreasing order, the largest squared values will come from the numbers with the largest absolute values. These numbers are located at the ends of the array. By comparing the absolute values at the start and end, we can determine which squared value is largest and place it in the appropriate position in the result array. Here's how this works step by step. We start with two pointers, one at the beginning of the array, called left, and the other at the end, called right. We also create a result array of the same size as the input. Then, we compare the absolute values of nums, left, and nums, right, square the larger of the two, and place that squared value in the last available position of the result array. We then move the corresponding pointer inward, either incrementing left or decrementing right. This process is repeated until all positions in the result array are filled. The beauty of this approach is that it only requires traversing the array once, giving it a linear time complexity of O(n). Additionally, it uses no extra auxiliary space beyond the result array, making it space efficient as well. This optimized two-pointer approach offers several advantages. First, it is significantly more efficient than the brute force method because it avoids the unnecessary sorting step. By leveraging the fact that the input array is already sorted, we can compute the final result without disrupting this order. The result is a solution that is both faster and more space efficient. However, there are some minor trade-offs. The two-pointer approach is slightly more complex to implement compared to the brute force method. While the steps are straightforward once understood, they require a bit more thought and care during coding compared to simply squaring and sorting. Nevertheless, the gains in efficiency far outweigh this minor increase in complexity, especially for scenarios with larger input arrays. After evaluating the options, we chose the two-pointer technique as the optimal solution for this problem. The primary reason is its efficiency in both time and space. The critical observation is that the sorted nature of the input array allows us to avoid sorting altogether. By directly comparing the absolute values at the ends of the array and building the result array from back to front, we achieve a linear time complexity of O(n). This is a significant improvement over the O(n log n) complexity of the brute force approach. The trade-offs for this method are minimal. While it may be slightly more challenging to code than the brute force approach, the dramatic reduction in time complexity makes it well worth the effort. Additionally, this technique avoids the extra space overhead associated with sorting, making it more scalable for large inputs. In summary, while the brute force method is simpler, the two-pointer approach is clearly the better choice for its superior efficiency and scalability. The problem we're solving is to take a sorted array of integers, which may include both negative and positive numbers, and return a new array containing the squares of each number, sorted in non-decreasing order. The main challenge here is to achieve this efficiently by leveraging the sorted order of the input array. To address this, we use the two-pointer method. The intuition behind this approach is that the largest squares will come from the values with the largest absolute magnitude, which are located at the two ends of the array. By using two pointers, one starting at the beginning of the array and the other at the end, we can compare the squares of these values and fill the result array from the largest square to the smallest. To implement this, we start by initializing two pointers, one called left at the start of the array and another called right at the end. We also create a result array of the same size as the input, initialized to 0, and a result_index pointer starting at the last position of the result array. This pointer will help us fill the result array in reverse order. While the left pointer is less than or equal to the right pointer, we compare the absolute values of the numbers at these positions, square the larger one, and place it in the result array at the index specified by result_index. Depending on which pointer provided the larger square, we either increment the left pointer or decrement the right pointer. After placing the square in the result array, we decrement result_index to move to the next position. This process continues until the left and right pointers cross each other, ensuring all squares are placed into the result array in sorted order. Finally, we return the result array. The two-pointer method is particularly efficient because it avoids the need for additional sorting by taking advantage of the input array's sorted nature. The design of this approach is rooted in three key insights. First, the use of two pointers is effective because the largest absolute values are guaranteed to be at the two ends of the sorted array. This allows us to systematically handle the largest squares first. Second, filling the result array in reverse order eliminates the need for shifting elements or additional sorting steps. Finally, the algorithm handles various edge cases seamlessly. For example, if the array contains only negative numbers, the pointers still move inward, comparing values correctly. Similarly, for arrays with only positive numbers, the natural order of the squares is preserved. When the array contains both negatives and positives, the absolute value comparison ensures the algorithm works as intended. The algorithm relies on a few simple yet effective data structures. The input array is used to access the original values that need to be squared. The result array is pre-allocated to store the squares in sorted order, avoiding any resizing costs during execution. The 2 pointers, left and right, play a crucial role in efficiently traversing the input array from both ends. To analyze the complexity of this approach, the time complexity is O(n), where n is the size of the input array. This is because each element in the array is processed exactly once as the pointers move inward. The space complexity is O(n) as well, due to the need to allocate space for the result array. Importantly, no additional data structures are introduced, which keeps the memory usage minimal. Let's walk through an example to solidify our understanding. Suppose the input array is -7, -3, -1, 4, 8, 12. We initialize left at index 0, right at index 5, and result_index at index 5, with the result array prefilled as 0, 0, 0, 0, 0, 0. First, we compare the absolute values of -7 and 12. Since 12 is larger, we square 12 and place 144 at result 5. We then decrement right to 4 and result_index to 4. Next, we compare -7 and 8. Squaring 8 gives 64, which we place in result 4. We move right to 3 and result_index to 3. We then compare -7 and 4, square -7 to get 49, and place it in result 3. This time, we increment left to 1 and move result_index to 2. Continuing, we compare -3 and 4, square 4 to get 16, and place it in result 2. We decrement right to 2 and result_index to 1. Comparing -3 and -1, we square -3 to get 9 and place it in result 1. Finally, we square -1 to get 1 and place it in result 0. The final result array is 1, 9, 16, 49, 64, 144, which is the output. This example demonstrates how the algorithm efficiently builds the sorted squares array step by step. This Python implementation leverages the two-pointer technique to solve the problem efficiently. Let's break it down step by step. 1. Initialization. The left pointer starts at the beginning of the array, and the right pointer starts at the end. We also initialize an output array, result, with the same length as the input array, filled with zeros. This array will store the squared values in sorted order. 2. Iterate from the back. Since the largest values, in terms of absolute magnitude, will dominate the squared results, we populate the result array from the last index down to the first. 3. Compare absolute values. At each step, we compare the absolute values of the numbers at the left and right pointers. The larger absolute value determines which number's square gets placed into the result array. If abs, nums, left, is greater, the square of nums, left, is stored in the current position of result, and the left pointer is increment. Otherwise, the square of nums, right, is stored, and the right pointer is decrement. 4. Repeat for all indices. This process continues until all positions in the result array are filled. 5. Return the result. Finally, the result array, which is now sorted, is returned. This approach ensures that we process the entire array in O(n) time, where n is the length of the input array. It avoids the need for extra sorting operations, making it both time efficient and space efficient. Additionally, the two-pointer method takes full advantage of the fact that the input array is already sorted, which simplifies the logic significantly. This is the Java implementation of LeetCode problem number 977, squares of a sorted array. The logic mirrors the given Python solution, using two pointers to iterate from both ends of the array and filling the result array from the back. Key differences include explicit type declarations for variables, the use of the math.abs function for absolute values, and Java's array handling. The implementation ensures optimal performance with O(n) time complexity. To solve the problem of sorting the squares of a sorted array, we start with the given input nums as -4, -1, 0, 3, 10. We initialize two pointers, left at the start of the array and right at the end. These pointers help us compare the absolute values of numbers from both ends. The result array, which will hold the sorted squares, is initialized with zeros and has the same length as nums. In the first step, we compare the absolute values at the left and right pointers. Abs -4 is 4 and abs 10 is 10. Since 10 is greater, we square 10 to get 100 and place it in the last position of result. The right pointer is then moved one step inward. Now, the result array looks like this: 0, 0, 0, 0, 100. Next, in the second iteration, we compare the absolute values of nums, left, and nums, right. Here, abs, minus 4, is 4, and abs, 3, is 3. Since 4 is greater, we square dash 4 to get 16 and place it in the second to last position of result. The left pointer is then moved inward, pointing to the next element. Now, the result array is 0, 0, 0, 16, 100. Moving forward to the third iteration, we compare abs, minus 1, and abs, 3. Since abs, 3, is greater, we square 3 to get 9 and place it in the next available position in the result array. The right pointer moves inward again. At this point, the result array becomes 0, 0, 9, 16, 100. In the fourth iteration, we compare abs, minus 1, and abs, 0. Since abs, minus 1, is larger, we square dash 1 to get 1 and place it in the result array. The left pointer moves inward again. Now, the result array is 0, 1, 9, 16, 100. In the final iteration, only one element remains, which is 0 at the right pointer. We square it to get 0 and place it in the last remaining position in the result array. The final sorted squares are 0, 1, 9, 16, 100. With this, the first example is complete. Moving on to the second example, the input array is -7, -3, 2, 3, 11. The left pointer starts at the beginning, pointing to -7, and the right pointer starts at the end, pointing to 11. Once again, the result array is initialized with zeros to store the sorted squares. In the first iteration for this example, we compare abs, -7, and abs, 11. Since abs, 11, is greater, we square 11 to get 121 and place it in the last position of the result array. The right pointer moves inward. The result array now looks like this: 0, 0, 0, 0, 121. In the second iteration, we compare the absolute values abs, -7, and abs, 3. This time, abs, -7, is greater, so we square dash 7 to get 49 and place it in the next available position in the result array. The left pointer moves inward. Now, the result array becomes 0, 0, 0, 49, 121. For the third iteration, we compare abs, -3, and abs, 3. Both values are equal, so we can square either one. Squaring 3 gives 9, which we place in the next position in the result array. The right pointer moves inward once again, and the result array updates to 0, 0, 9, 49, 121. In the fourth iteration, we compare abs, -3, and abs, 2. Since abs, -3, is greater, we square dash 3 to get 9 and place it in the next available position in the result array. The left pointer moves inward. The result array now looks like 0, 9, 9, 49, 121. Finally, in the fifth iteration, only one element remains, which is 2 at the right pointer. We square it to get 4 and place it in the last remaining position in the result array. The final sorted squares for this example are 4, 9, 9, 49, 121. Now, let's look at the third example, where the input array is 1, 2, 3, 4, 5. The left pointer starts at the beginning, and the right pointer starts at the end. The result array is initialized to all zeros, ready to store the sorted squares. For the first iteration in this example, we compare abs, 1, and abs, 5. Since abs, 5, is larger, we square 5 to get 25 and place it in the last position of the result array. The right pointer moves inward. The result array now looks like 0, 0, 0, 0, 25. In the second iteration, we compare abs, 1, and abs, 4. Again, abs, 4, is larger, so we square 4 to get 16 and place it in the next position in the result array. The right pointer moves inward again. Now, the result array becomes 0, 0, 0, 16, 25. In the third iteration, we compare abs, 1, and abs, 3. Since abs, 3, is larger, we square 3 to get 9 and place it in the next position in the result array. The right pointer continues to move inward, and the result array updates to 0, 0, 9, 16, 25. In the fourth iteration, we compare abs, 1, and abs, 2. Since abs, 2, is larger, we square 2 to get 4 and place it in the next position in the result array. The right pointer moves inward, pointing to the same position as the left pointer. The result array now looks like 0, 4, 9, 16, 25. Finally, in the fifth iteration, only the number 1 remains at the left pointer. We square it to get 1 and place it in the last remaining position in the result array. The final sorted squares for this example are 1, 4, 9, 16, 25. With all iterations complete, the final output for the third example is 1, 4, 9, 16, 25. Each example demonstrates that the two-pointer approach efficiently sorts the squares of a sorted array. By comparing the absolute values at both ends, we ensure that the largest squares are placed in descending order from the back of the result array, eventually resulting in a fully sorted array of squares. The time complexity of this algorithm is O(n), where n represents the length of the input array nums. To break this down, we begin with the initialization step. Here, setting up two pointers, left and right, is an O(1) operation, and creating the result array of size n requires O(n) time. Next, the main loop iterates from the last index to the first, completing n iterations. Within each iteration, we perform a fixed number of constant time operations, comparing the absolute values of nums, left, and nums, right, assigning the larger squared value to the current position in the result array, and adjusting the pointers. Each of these steps takes O(1), so the total time for the loop is O(1) multiplied by n iterations, which simplifies to O(n). Finally, the return statement, which outputs the result array, is an O(1) operation. When we add these steps together, the overall time complexity of the algorithm is O(n). Now, let's examine the space complexity. The space complexity of the algorithm is O(n), and this is primarily due to the result array. The input array nums itself is read-only, so it does not contribute to the space usage of the algorithm. The result array, however, is initialized with n elements, which contributes O(n) to the space complexity. Additionally, the scalar variables left, right, and I used for tracking positions and iterations are simple values that require O(1) space. Since the result array dominates the memory usage, the overall space complexity is determined to be O(n). To compare, the brute force approach involves first squaring all elements in the input array and then sorting the squared values. While squaring the elements takes O(n), sorting the array adds an O(n) asterisk log n step, resulting in a total time complexity of O(n) asterisk log n. The space complexity in this approach remains O(n) due to the size of the output array. However, the optimized two-pointer approach eliminates the need for sorting by leveraging the fact that the input array is sorted, though it includes negative values. By using two pointers and filling the result array in reverse, the algorithm achieves a linear time complexity of O(n), while maintaining the same space complexity of O(n). Importantly, this optimized method ensures consistent performance across all scenarios, with an O(n) time complexity in the best, average, and worst cases, as every element is processed exactly once regardless of the distribution of positive and negative values. To mathematically confirm the time complexity, consider that the algorithm processes an input array of size n. The main loop runs exactly n times, and during each iteration, it performs a constant amount of work, including comparisons, squaring, and pointer updates. Since each iteration involves O(1) operations and there are n iterations, the total work is O(1) multiplied by n, which simplifies to O(n). Additionally, there are no nested loops or recursive calls, so the overall time complexity is conclusively O(n). Similarly, for the space complexity, the algorithm uses an output array of size n, contributing O(n). The scalar variables left, right, and I require only O(1) space, and no extra data structures are introduced. Therefore, the overall space complexity remains O(n), dominated by the size of the output array. When solving this problem, it's essential to avoid some common pitfalls. First, one major mistake is not leveraging the fact that the input array is already sorted. Many solutions square all elements and then sort the results, which unnecessarily increases the time complexity to O(n) asterisk log en. Instead, we can solve this in O(n) time by using a two-pointer approach. Another common issue arises with negative numbers. Squaring negative values can produce results larger than squaring positive numbers, which can disrupt the ordering if not handled correctly. For example, squaring -3 gives 9, which is greater than squaring 2 to get 4. Finally, edge cases like arrays that are entirely negative, entirely positive, or even empty are often overlooked. These special cases can affect how the two-pointer approach works, so testing thoroughly is critical to ensure correctness in all scenarios. Another common mistake is the inefficient use of space. Some solutions involve creating unnecessary intermediate arrays or data structures before sorting, which increases the space complexity. This problem can be solved with just O(n) space if we use a result array intelligently and avoid redundant operations. Additionally, off-by-one errors are a frequent issue when implementing the two-pointer technique. These errors occur when the pointers skip over indices or overlap, leading to missed elements or incorrect placement of the squared values in the result array. Properly managing pointer movements and ensuring all indices are covered is key to avoiding this problem. Now, let's discuss some useful insights for interviews. This problem is a great example of leveraging sorted inputs with a two-pointer technique, a fundamental pattern that appears in many array-based problems. It's also important to emphasize thorough testing of edge cases during interviews, such as arrays with only zeros, all negatives, or both negative and positive numbers. These scenarios can reveal weaknesses in the implementation. Be prepared to explain the time complexity of your approach. Specifically, you should highlight how the two-pointer method achieves O(n) complexity compared to the O(n*log(n) of brute force sorting. Finally, discussing the trade-offs between time and space complexity is valuable. For instance, explain the use of O(n) space for the result array and whether in-place modifications are feasible under given constraints. This problem connects to several related problems that also use two-pointer techniques. For instance, LeetCode 15, the three-sum problem, requires finding triplets that sum to 0 in a sorted array. Similarly, LeetCode 16, three-sum closest, builds on this technique by focusing on finding the closest sum to a target value. Another example is LeetCode 18, the four-sum problem, which extends the two-pointer strategy to handle a more complex variation. Of course, LeetCode 977 itself, squares of a sorted array, is a classic example used to practice and master two-pointer methods. These problems share common themes and are excellent for building a deeper understanding of array manipulation and optimization techniques. Finally, let's compare some alternative approaches and their trade-offs. The brute force approach involves squaring all elements and then sorting the array. While simple to implement, its time complexity is O(n*log(n) due to the sorting step, and it uses O(n) space for the result array. On the other hand, the two-pointer approach is more efficient. By comparing absolute values at both ends of the array, we can determine the order of squared values in O(n) time. This method also uses O(n) space for the result array but is optimal in terms of time complexity. Lastly, there's the option of in-place modifications. This strategy avoids using extra space, reducing space complexity to O(1), but it can be harder to implement and debug. Edge cases become particularly tricky with in-place solutions, so they require extra care in testing. Great job on completing this problem walkthrough. Today, we learned how to efficiently solve squares of a sorted array using the two-pointer technique. This approach is not only time efficient but also demonstrates the power of leveraging array properties in problem solving. Keep practicing and applying these concepts to similar problems. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!